And thanks for bearing with me, you guys, dragged in for a second seminar. So this one is more of ideas as well. So maybe there's some discussion points in the current theme of getting enmeshed in some nice academic discussions. Maybe this can be part of that. And Mike says there's a fair time between this and Chelsea buns at afternoon tea, so there's time. I was only going to have a very short session for today, but we'll see. Anyway, so I am only planning for about half an hour for today too. So the main points for this one, partly it's based on whenever someone brings a picture in front of you, if you take a picture to an audience, then someone's going to ask, is it really there? Is what you're saying, is it really there in the picture? And those notions really relate back to statistical inference. And there's a bit of a gulf between graphics and inference, but there shouldn't be. It's a part of that. So some of the ideas from inference we're bringing into graphics is the goal here. And really these ideas come from Andreas Buyer, who gave a talk in '99 at JSM, and I'm just shamelessly using his work. Okay, so why is this important? Here's an example that goes back to Anscombe, I think, in 1973, in terms of regression analysis. If you look at all of these four plots, they're completely different, but the correlation for all of them is 0.7. Okay, so correlation as a measure is only appropriate really for measuring that top left one. But nevertheless, we always report correlation for pairs of variables. But in these other cases, there's a lot more information going on, and that's the reason why you want to make pictures and you want to use pictures in analysis, right? So we can not only say that the correlation doesn't summarize the association here, but we can also say why it doesn't summarize the association. Okay. Right, so generally what's inference? So here's one definition from answers.com. The process of reaching conclusions about a population on the basis of random sampling. It's what we're doing all the time, right? So I don't know if anyone wants to say anything else. It's not it's more qualified people than me here. But when we say,
certainly a general definition.
Sorry?
Certainly a statistical definition. But doesn't the word inference go well beyond statistics?
Give us an example then.
Well, maybe we discuss this offline.
No, it's a good idea, I think, really. So yeah, inference. When you think of inference.
For the particular to the general?
Yeah.
So from a particular example or from some clues, you're making some assessment of a larger situation.
Right.
Yeah.
Those don't necessarily need random sampling.
It could be on the basis of evidence.
Yeah.
Yes.
So sorry, go ahead.
It could be on the basis of evidence rather than random sampling.
Sure. Okay. So you might have different sorts of evidence instead of random sampling. Yeah. So we may not always have a random sample, but we may have some subset or some clues evidence. Yeah, it's not a great definition, but
it could also be about a fixed unknown, like a physical constant, rather than a population. So
say that again.
it could be an unknown, like a physical constant, like big G or something, which isn't a population. But I think that's still a problem.
Right. It still would be considered a parameter, though.
Yeah, I'm just saying it's broader.
Yeah.
But you could look at Newton's Newton's laws of motion, giving something that's flying through the air. You can infer when it's going to hit the ground.
Right. So, but generally, as part of trying to understand our surroundings and make sense and organise our world, inference is one of our key activities. And we have various processes in statistics. One process is the hypothesis testing framework. You have a null hypothesis, alternative hypothesis, and you gather evidence. You calculate your probabilities on the basis of your null in order to test your null, right? So we generally have a hypothesis testing setup, test statistic that's calculated on your sample, which forms part of your evidence. You might have a p-value, and on the basis of that, you make some sort of decisions and conclusions. So that's sort of the framework that we're putting underneath here too. Right, so let's look at a scatter plot as an example. By the action of making a scatter plot, you're asking the question, what is the relationship between x and y? So implicit in that could be a null hypothesis that x and y are not dependent, versus an alternate that x and y are dependent. Right?
I'm looking at a residual plot.
Okay, exception. Right, this is great. This is why feel free to argue with me. Right. Yeah, it's not the only purpose of making, well, in a sense, some way, if you're making a residual plot, you'd like to see that there is no dependence in your residuals, right? Or other sort of structure, yeah. But yeah, you want the null to be true in that situation.
I can look at a scatter plot to think about whether dependence is linear versus non-linear. Null.
Okay, and so then it's not quite this. So yeah, it's sometimes we have a little bit more tailored, that you want to see if the relationship is linear versus something else. And that's a little bit more specialist. So this is not that, yeah, but you're right. There are other null and alternate hypothesis pairs that we could pull together, right? Okay, the test statistic for this is the scatter plot itself, right? That's our test statistic. Just like we can calculate test statistics for all sorts of things, when you make a graphic, that's a test statistic. It's your sample that you're looking at, and that's a particular piece that you have to work with. All right, so one way to think of that in terms of the hypothesis testing scenario is, if the null hypothesis were true, like if there is no dependence between x and y, what might a scatter plot look like? Okay, what might the scatter plots look like? Right, and then how does that test statistic, so our actual scatter plot, compare with those null plots? Right, so in order to look at this, you need to have some process for generating scatter plots that are consistent with a null hypothesis. A couple of prime ways we do that generally. Permute one column to break any association. So then it's sort of a non-parametric approach. You just take, if there's an association between x and y, if you take one column and scramble those values, that association is broken, right? Or simulate from a known distribution. So if you are really interested in whether the association is linear, that second one, simulating from a known distribution, might be the appropriate way to generate null data to compare your plot with. Right? I mean, these are standard sorts of ways of dealing with problems in statistics anyway. Okay, so here's your first test. I've got 9 plots here. You've got 2 questions to answer. First is, which is the most different plot of the 9? And second, why is it different, or how is it different from the others? Now, actually, just wait for a sec, or write it down. Actually, maybe write it down is a good thing on that little scrap of paper. Did everyone get a scrap of paper?
You didn't give us pens.
Oh, I forgot about that. Yeah, details, right. Dear, dear. Should I go and
I'll
grab?
remember.
Well, I've got a whole bunch is the problem. That would be great, actually. Right, everybody got it? Got an answer? Which is the one that anyone still thinking about it? It's not completely simple. Pardon? Mike?
I'm still thinking about it.
B1.
Yeah, B1. All right. Why?
Because I can't visually see the difference what's going on in a big blob, but all of them have the same 2 outliers except B1, which has a different outlier.
Yeah. Brilliant, right? So, I mean, there's this big blob, and we might be looking for things in there. Maybe there's some differences there too, but the consistent thing with all the other plots is that there are 2 outliers instead of 1. Yeah, you got it exactly. Any questions for anyone about that? Right. All right. So, in terms of looking at association between 2 variables, the only thing in the real data that makes the 2 variables dependent is that 1 outlier. All the others are generated here by permuting 1 column. So it's easy enough to see how we managed to get 2 outliers and everything else because of change the association from the 2 large values to 1 large value, 1 small large value. Okay? Right, we're going to do that with a whole bunch of pictures next.
So all of these are just permutations of the outliers.
Not necessarily. So in each of them, 1 plot is real data and the other 8 are generated under a null scenario. I'm not going to tell you what my generating process is necessarily. So I think that can also bias your thinking about it too sometimes. Right, so as I said, I think you all chose B1 as a different one. I hope so. There is differences of way people see things. And the reason you gave is that there's only 1 outlier in the top right centre, and all the others have the 2. So X and Y dependent only because of the single point.
This conclusion is about the E1 plot, and the others are going to be permutations.
Okay, so for all of these additional pictures, I want you to do 2 things. Choose the plot that appears to be most different from the others to you. They're all set up the same, so it's ABC, 1, 2, 3. And then also write your reason. Okay, and it's then some are easier and some are not so easy. So it's okay, it's not a test of you.
So you're framing this as sort of like a pattern recognition thing without the context of the data analysis that is behind it. That's the puzzle here.
Yeah. Okay, so number 1. This is a warm-up.
Sorry, what's in the inside the circle?
Oh, yeah. So I can give you a bit more information about these. Each of these are projections of 6 dimensions. So they are the best projection for separating the 3 groups. But so, this is a projection of 6D. That's all. And maybe I should take that off in general, but I think it's useful here to some extent. Anyway, this one's a no-brainer, but you got that.
The scales are always the same?
The scales, you have to be careful with all sorts of things like that, but yeah, scale will be the same. Yeah, this is not a trick question. This is, yeah. Question? No? Right, here's your next one. You do need to write an answer. It's a hard one, yes, I think. I agree with you. But you need to pick one and you need to tell me why. Had enough time, or you need more time? 3.
You've got these by permuting columns in certain ways.
This is a permutation one, but yeah, just ignore that for now.
Okay, I should just.
Yeah, it just is any plot different, or pick the most different to you and just say why. Okay. Ready for the next one?
Informational question.
Yeah,
B2, are there supposed to be 2 dotted lines there?
there are. There are 3 dotted lines. I mean, there's 1 solid line and 2 dashed lines.
All right.
I have no context to distinguish black solid from dashed. We should treat them.
They are 3 different groups. Yeah, they do represent different groups. Yeah. Again, I think I'm going to have you just try to make a judgment on the basis of pattern, just pattern recognition, as Ian says.
We bring way too much prior knowledge to this.
Pardon?
We bring way too much prior knowledge.
It's a problem of being overeducated at times. I think I might agree, but
Could you with the pointer show where the top dotted line is on B3?
on B3, yeah, it's pretty much underneath the black line. Yeah, it's the only one that's sort of a little bit out from that one is the red large dash. Yeah, but it pretty much mirrors the black one. Enough time? Ready for the next one? Just think we've got some Chelsea ones coming. If you get it right, you get 2 Chelsea ones.
Get wrong, you get
3,
three.
4.
Are they
Pardon? Sorry?
I was wondering where the Chelsea buns were from.
Oh, there.
They live above the bakery.
There's a famous bakery called Fitzbilly's. Yeah. Well, at least that bakery is famous for Chelsea buns. But. Okay, so work this one out.
Sorry,
This is a hard one too. Yeah, no collusion. Ready for the next? Nope. Good. Okay. All right, this is a tough one. They're all moving, and they all move it. So this is going to be extremely difficult, I think, but see what you can do with it. I'll run it a few times.
Variable here?
Pardon?
Is time an important variable?
Only in the sense of having lots of pictures of the same thing, same object. Instead of just one projection, you're seeing a bunch of them for each object. This one might not be.
Saw these last week.
No, we didn't see these ones. But yeah, it's tours. But each one is just a pretty small time fragment of a tour on an object. Sorry?
I've never been able to get my head around tours.
I'll give you a clue with this one too, that we're interested, of course, in the differences between the three groups. Whenever there's colour there, that's probably one of the primary things that you're trying to see as being different. Enough of this one?
I'm going to protest on this one because not only is it not what's the question, what's the answer, it's not, we don't even know what the question is.
Does this question is still, is any one of these more different than the others? Or which is the most different from the others? So it's the same question. Yeah, I mean, it's hard because I've given you packed a lot in each one, and I haven't synchronized times, so it may be too difficult, but I am curious. It's still the same question. Enough? Okay.
And it's intended that we can't read the lettering.
Yeah. Enough time on this one? Alrighty. So I've got one more, but I wanted to just say a couple of things before we look at that one. The whole workshop is about high dimensional data, and graphically we've talked about fairly low dimensional so far, but you've actually just seen some high dimensional tests in here too. But one common approach to plotting a very high dimensional data is using a heat map or a colored matrix. It's got a bunch of different names, or an image plot, where you take the matrix of data and just color each cell according to the numerical value that's in the cell. It's a very, very common way to plot very high dimensional data. So a couple of precursors to that. If one of the purposes is to get an overview of the data, it's why we're doing plots of data, is to get some sort of overview of what the whole big picture is. We looked at, showed you something on tours last time, which is pretty nice for relatively low dimensions and real value data. So you're looking at a lot more projections than just a single principal component projection or a single LDA projection. We're looking at a bunch to try to look at from all sorts of sides to see what possible pieces are in the high dimensions. With a heat map, so tours really aren't feasible when you've got 200 dimensions. Space is too big. So the most common way that people plot high-dimensional data is to take the matrix and color the cells. So I've got one test with heat maps, and I've got more to say on this in a few slides. Okay, so here's your last test. Same problem. Which one of these is the most different from the others, and why?
One of the ones where if you stare across your eyes and you can see something in it.
It's not quite that bad. No, there is not a hidden picture. But yeah, that's the problem with heat maps. Is to me, I've got to find something in there with squinting my eyes and opening and shutting them a bunch of times, or looking cross-eyed or something. It's not hidden that much.
What's your color scheme?
Red to blue, color brewer colors. I think red's high and blue's low here.
Magenta and red.
Pardon? And the white is zero sort of color.
What is magenta?
So really dark red is really high. There's not magenta in here. I mean, if you got red and blue right next to each other, maybe you're sort of merging it to magenta. But there's 72 cases and 40 variables here. Be a common way to do it. All done? All right. Let's go back and check your answers then.
Can we mark our own?
You're marking your own. But I'm curious to see what everybody put first. So I do want to collect these at some point. So this one's easy. It's an A2 because they're three very well separated clusters corresponding to color. And so you should have both those reasons. This one here, I didn't mark these on because I didn't want to accidentally show you the answer at any time. So it's, there's my, I don't think I have my cursor. Oh, hey. It's this one here. No, I don't know how to get rid of that. Okay, so it's actually this one here.
Why?
No real reason, it's just that's the real data. The real data in this case is actually nonsense data. The real data here is 50-dimensional data with 3 randomly generated classes. There is no structure in this data. So in some sense, this is reassuring. I would guess that I'm actually hoping that you all put different things. Maybe not. Maybe there's something in one of these pictures that people clued to, or... sorry, Steve?
They're not randomly generated because I can distinctly see that circles at the top, the purple in the bottom, and the orange on the
These are 3 random classes, and I've got 50 dimensions. And I'm looking at a 2-dimensional projection, actually the best 2-dimensional projection of 50 dimensions. And yeah, it does look like, hey, we've got 3 nicely separated clusters corresponding to the 3 classes. That's the interplay of dimension and structure. Right. So with more dimensions, it's possible to see structure that's really not there, really isn't there. So I think one also should probably keep a record of how long it takes people to come to an answer, because when they struggle with something like this, which is I think what you did, there has to be more doubt about whether people can see the structure or not, right?
Did you cluster the data and then work out the canonical variates on the basis of those cluster labels as if they were true or something?
Oh, this is just projection pursuit, using like an LDA type index to find each one. Yeah. So it's sort of the best low dimensional view that separates the 3 groups. Yeah. Okay. I don't know, did anybody put that one? What were some of the answers? A1? Anybody put A1? A2? A3? B1? B2? B3? C1? C2? C3? Okay. All over the map, and it should be. What about this one? This is the correct answer.
Correct according to what criteria?
Real data. So there is a correct answer because there's real data. And the rest of the plots are generated under the null scenario. So I know which is the real data. So because I know that's the correct one. So it's not really a test of you. It's whether you can pick the real data. So it's a test of the structure in the real data is what we're aiming for. So this is the real data. These are longitudinal measurements on, we actually saw it last week. This is wages and experience. And the 3 groups are black, white, and Hispanic. And a lowest fit to the different races. So the rest of these are generated on the basis of taking those race labels and scrambling the race labels and recalculating the low S for that scrambled race label. So in here I've got 3 races, but they're purely random. Okay. So how many people picked this one? See, you guys are good. Right, why?
But my reason was totally different. I
Yeah.
was thinking of QQ plots. The dotted ones are error bars for a theoretical distribution. The true one was the data, and that one just missed right in the middle of the distribution.
Okay.
Totally different, right?
Overeducated.
I read that the black line diverges earliest,
Voila.
and they're the most different lines.
This one here, yeah. So someone else seems like they said that too. Yeah.
Separation.
Best separation. Yeah. I think this is the difference between blacks' wage experience than the other 2 the other 2 races actually in the data that I've got. There seems to be this mid experience level plateau for blacks. Over in this area over here, you'll see the separation over there in quite a few of the pictures. There's not a lot of data over here, and so there's a bit more spread. So that particular part of the structure isn't really significant. Right. Okay, this one. This is the correct one. C1 is the correct plot. So that's the real data. Did anybody pick it? 3 people. Good, why?
Behind the lower left is the most outlying.
At the outlier, the vertical line.
Okay, yeah, that's the reason, this guy. Well, I mean, we don't, that particular thing, I don't know, this is what I have to gain from what people say actually, about why they're queuing to that plot. What other...
Queued to it for a reason that I couldn't really justify since I didn't know what the purpose was. So, I'm not sure that it's informative that I picked it.
Sure. And I think that's going to, I mean, that you can't guard really against that anyway. We can't always explain why we do things, right, at times. What about, who picked some other picture as a...
B2.
I picked B2.
B2?
Because of that gap at the top right, and it's
That top right is a bit empty.
I queued to it for those 2 lines of points that
Bottom.
just look pretty.
So you said B2 as you also said B2?
Yeah.
Because there's sort of more...
Because of that V shape of 2 lines of dots that are
bottom right.
in the bottom right of the plot.
Okay. What other choices were there? Just those 2? There is quite a bit of structure in these pictures, in this data itself. One of the first things that I was interested in, this is corn yield versus one of the minerals in the soil. And I was curious that as boron increases in the soil, the yield gets consistently higher. And so I thought that this is the important structure. But if we take yield and boron and scramble the association, that's there a lot of the time, that skewness. It's a product of skewness in both directions. I think it's not that rare a structure. The only thing that's really rare is this guy. But again, it's not, I think it's not a clear-cut structure as well, and so there should be some doubt in terms of what I get returned from people's judgments on this as well, would be my guess. That it's not easy to say that this one is clearly different to the others, and I'd expect to see a little bit of differences in which ones people pick. But okay, the correct answer is A1. Did anybody pick that one?
I was distracted by points clouds exploding at unpredictable
Yeah,
times.
it's not an easy one. It's the first time I've done something like this. I just wanted to see what happened this time. Yeah, maybe there's too much happening in each of these. The only reason, if you just look at that single projection, that last one, so basically what I've done is take the optimizer and say, find me the best projection, and shown you a few other things along the way, and done that a few times in each of these examples. This is gene expression data, and I've got, there's 70 observations in 40 dimensions. It's the same one as the heat map, actually. And A1 is the real data. There seems to be some difference in the 3 cancer classes. I think it's slightly more separated there than in all the others where the points are just permuted. But again, it's a high dimensional 40 dimensions with 70 cases, so you'd expect to see some differences between the classes. So we'll leave that one there. Actually, it would probably be easier if I demonstrated just showing that one in a big window and then permute the classes and show you what happens when you permute it. The optimizer has a lot more difficulty trying to find a view where you've got 3 classes separated. So it almost, even though there's a lot of dimensions there, it looks like there is some signal to the gene expression, to the cancer classes, as opposed to just noise. In this one here, the correct answer is B3. Did anybody get that one? You got it?
Yeah.
Why?
Is it because in the 4th column it's got those very regular little lines?
In the 4th column? This one? Or, sorry?
fourth column, all the lines are very similar.
Right, they're all about the same amount.
I had two answers. That was one of them for that reason.
For that particular reason?
Yes.
Yeah, okay.
The other answer was C1 because it looked like the most monotonic.
C1. Okay. So monotonic in here.
It seemed more like fat to narrow from top to bottom for that one than the others.
Okay. Any other?
I thought C2 because the first column was very dark.
Because it's more,
Darker.
the whole column's darker. Okay.
It stands out. But maybe it doesn't.
Any other selections?
Well, A1 because the last column seemed to have things at fairly regular intervals at the bottom, down the bottom.
At the very last one, okay. This is real data again. This is data from an ecologist that I know, and they're collecting insects on different plants, and they want to know whether there's really association between the insects and the hosts. And I want to see is there anything here, because it didn't look like there's a lot of preference from species to host, right? There's always a problem of when you've got strange marginals. So in here we've got host and species. The marginals have a skewed distribution, and it can sort of makes it hard to pick up association between the two variables when you've got some structure in each of the marginals. If you look at this one, in the first column, I think it's less monotonic than the others. It's sort of the first column where they've got the bigger numbers.
The blobs indicate frequency, do they?
Yeah, so these blobs are counts in this case. So
Actually,
blobs are proportional to
two-way
counts.
frequency table, in fact.
Yep. Okay, so they sort of wobble in and out a little bit more than the other ones. And again, everything's generated by permutation in this case, but at least that's.
So you told us the right answer?
I told you the answer. B3 is the real data. Yeah, but there's a lot of noise, so it's not. I think I convinced myself there's a little bit of structure here. There's a little bit of association. So maybe it's worth continuing on the analysis with this data. Okay. And this one here, the correct answer is C2. Who got C2? Why?
Because on the top
Corner.
row, on the left-hand
Gee, you
side.
guys are good. Now, see, I have problems with heat maps, but yeah, there's a structure. So actually, in the end, I simulated this data. So I had hoped to do the same data as those little tours that gave everyone a headache before, but I could not get a reordering of the data matrix so that the differences in the classes popped out. So I simulated some data where I've just got random normal, and for these 6 variables, for these 20 cases, I've shifted one group by 1 point out. Okay, so in 6 of the 40 variables, there's a little bit of difference between the classes. Okay.
So the usual clustering doesn't work?
Pardon?
Usual clustering of the rows and columns didn't work with the real data?
So, yes, in terms of that they're organized in terms of the classes. Right, but it's a little bit tricky in this case. These ones are just permuted on the assumption that the first 20 rows are my class 1 and the rest are otherwise. So I'm not well, anyway, so yeah, the ordering you think of in terms of all of one class are at one end and all of my other class the other
Also
one.
because of the variables with the
And-
sigma are all together.
And the 6 variables that have structure are all together. Yeah, very important. Okay.
I've seen Seurat's original painting.
Pardon?
I think I've seen Seurat's original painting.
Right. Yes, you can imagine there's plenty of scope for reinventing art too here. Okay. Significance. Each plot has, or the real data has a 1 in 9 chance of being chosen by the judge. Right, so each of those examples. And so we might make a test for how important the structure in the real data is by taking a sample of judges, which is you guys in this case. And all of you need to have not seen the data before. So you need to be uninvolved, impartial, and viewers. You don't have anything invested in the data analysis. Right, on the basis of that, we might be able to get some sort of assessment of how significant that structure is. Right, pool your answers. So in practice, I don't go that far. In practice, I use these ideas, but I'll generate null plots myself and just stare at them myself. That's a very biased view, but sometimes the structure is so obvious, I'm just not going to bother. It just gives me a sense that there's something there. Yeah.
So I'm worried about the sort of the framing bias aspect of this.
Yeah.
Because if you sort of go around and say, which would you like to have on your kitchen wall, you're going to get a different set of answers in evaluating your randomly generated plots than if you frame it some other way.
Right. So any time that you involve people in judging things or doing questionnaires, you have to be very careful with your language. Yeah, you're right. Okay. So getting beyond that, though, if I'm in doubt about the reality of the structure, I'll go out with a whole bunch of plots around the corridors and get my office mates or students hanging around to tell me something, which is what I did with that ecology data. And more often than not with that particular sample, people seem to get it's a little bit of uncertainty there, but they seem to get the real data and tell me why that was. There wasn't quite as a big a gradient, which is how I convinced myself that, okay, I go back to the ecologists, we'll keep working together on this data. Okay. So generally, if you want to have some more objective help, I don't know if we can bring computer vision into this, or I mentioned to some of you at times that there's this service by Amazon called the Amazon Turk, right? And that comes from this old story of the Turk, which is a chess-playing automaton in the 18th century, which was made by this guy, Wolfgang Kempelen. He toured Europe, beating various people, playing chess, until he was revealed that he actually had a chess champion in his machine, and it wasn't an automatic machine. Right. Okay, so Amazon has a web service where you can sign up to get people to do things for you. It's called the Amazon Turk, and I could do just the same as you guys here. I could put these pictures up here, and I pay anyone who logs into Amazon who's willing to tackle this task 2 cents per picture. They evaluate, and I eventually build up some p-values for things.
Huh?
Yeah, right. So the purpose of it is because it's recognized people can do things better than machines sometimes. Artificial intelligence is called. It's a great idea.
Is that double negative?
Sounds a little bit like that. Yeah. Anyway, this is Heike Hoffman and Hadley Wickham were playing around with this for a while. Okay, a little bit more on high dimensions. There are alternatives to heat maps. The fluctuation diagram, so what I showed you before for the ecology data is a fluctuation diagram where instead of color for each cell you use area. People are better at matching area to numerical value than color to numerical value. So there are alternates. The problem is that we're only looking at marginal distributions with the heat map displays. And the key is that you need to have a lot of ways to rearrange the heat map in order to extract structure. So looking at one heat map It's the same as if you're doing multivariate analysis and only looking at a principal components plot, looking at one view only. You have to have ways to rearrange, reorder those marginals.
Want a bit of clustering of the rows and columns.
And clustering, right? Clustering is one way to reorder. But really you need a whole bunch of methods in there and reorder a bunch of different ways to pull out things, right? A couple of things. You only saw this guy because I made this a little bit harder. So I just added a few more dimensions. There's 200 variables and 72 cases. Now,
And we saw it because you had the 6 variables which had the signal
yep.
together, but if you sort of randomly moved them along, so we wouldn't see anything.
Yeah, here. So if I hadn't done that for you, good luck. Right? So we often see the final product that people put in a paper with the clusters, where they've revealed something to us. Whether it's a real thing, I don't know. I've got plenty of examples where it's not quite the case. So you have to have some way of reorganizing. There's typically no reason why A is next to B is next to C on any of these. I don't know if you've got good eyes, you might see some things in here. I could have made it a little bit easier for you. There is something in here. Can you see? There's a bit of a divide here.
Yeah.
Slightly redder there than bluer here. Yeah, good. Anything else?
More above the line than below.
Yeah, right. More above than below. It's sort of a little bit bluer in this quadrant and redder up in the top quadrant. Okay, good eyes. Yeah? These are the sorts of examples that we see in the gene expression literature all the time, only much more extreme, where we'd see blocks of structure that people say, oh, cluster 1, cluster 2, cluster 3, etc. This is purely spherical data. It's purely Gaussian. I just turned it on its end. So I just chopped the largest values and laid the largest values here in the middle and the smallest values on this side. So I reorder it to make you maybe think there's something there. And I think we can play that game with any data. I can give you an arrangement where it'll make you think that there's structure in the heat map when there really isn't. And so that's one thing that I'm very dubious about in terms of heat maps. If I'd also changed the color mapping, someone asked about the color mapping too, if I had used some sort of function on the way I mapped the numerical value to color, I could have made this even more extreme. So you would just jump out of your seats and say, hey, cluster 1, cluster 2. But there's you have to really look at more than one arrangement in order to be have some sense for the reality of the structure. High dimensions too. Okay, so one more comment on high dimensions. Another thing is when you've got a lot of information, the small structure disappears. Outliers, minorities, small clusters or needles in your data. So if I've got an outlier in the gene expression data, which is exactly the sort of things I'm trying to find, that the genes that are more different in one treatment than another, just one, that guy will be lost in a heat map. If you think about bar charts, if you've got 200,000 people in a bar chart and only one has got a particular characteristic, that guy's going to get lost in an area plot. So any time that you've got a huge amount of information, small structure gets lost in the pictures. There are times that we need to have more than marginal views, and this is what we trade off with some of the numerical procedures, trading off the covariance from purely diagonal with some sort of compromise with more covariance estimated. And whatever you use, at some point you run out of screen space. So if you get 2 million points, you don't have enough pixels on your screen to put in there anyway. So, okay. So just summarizing, plots can be a test statistic. The null hypothesis is usually implicit from the type of problem you're studying or the type of plot that you're using. We can often have a process that will create a process that's will generate data consistent with a null to produce comparisons. And if we can get additional information from people about why they think it's different, we can provide some more information about the type of structure that's different. And then just lastly, this is not supplanting any sort of traditional analysis, it's just supplementing what we always do. So that's it. Thank you again for listening. It's lovely to come.
If anyone's got a comment.